Although we have talked about dynamics on networks, this video starts our in-depth discussion on dynamics of general systems. And so when we're describing the dynamics of these systems, the method that we're going to turn to is using differential equations to describe that behavior. And so the behavior that we're trying to model is the state, x. This is a function of time typically. And so the way that the system evolves is described by this differential equation. So depending on how we define this differential equation or what properties this differential equation has, it makes us analyze it in different ways. And so probably one of the more generic forms would look something like this, where the derivative, in particular the ordinary derivative, of the state is described as some function of both time and the state. And so the goal here is to convert from this kind of just general rule about how the state changes in terms of both time and state, the current state, and turn that into a trajectory, which is just the state as a function of time, and that's the solution. Sometimes we might talk about t as being the independent variable, typically because time is our independent variable, and the dependent variable then is the state. So right now I'm just showing this as a single state, and so this means that this is a first order because there's just one derivative. It's an ordinary derivative, so it's a first order ordinary differential equation. And we haven't made anything that specifies it further. For example, this function f could be a linear function, or it could be a nonlinear function of t, of x, of t and x. And so now what we're going to do is we're going to kind of reduce this set. In general, dynamics could be written like this. What we're going to do is we're going to make this more specific. So the first thing that we can talk about is making it autonomous. And autonomous simply just means that this function that describes the derivative of the state does not have any explicit dependence on t. So there is going to be dependence on t implied through the state x, because x depends on time, but you're not going to have any forms. F isn't going to have any terms like t squared, square root of t, t times x, and so on. And so that means that the independent variable t is not present in the expression of the differential equation. Now what we can do is we can chain together. Typically their system can have states. It can have more than one state, and those states can be interrelated. And so the change in one state could affect the change in the other state. And so that means that we would write them as a system of, and I left this out, but coupled autonomous differential equations. So autonomous, that nothing depends explicitly on time, and the derivatives now, I'm just writing them as a dot, a single derivative as a dot. And so it's a system because f1 and f2 in general depend on both states. So that means you can't solve x1 by itself because it's going to be dependent on what x2 is. So you have to solve these systems together. And so this describes essentially the format of what we're going to be talking about in the class. We will talk about some nonlinear systems, but the first way that we're going to start out is just by talking about a linear system of autonomous differential equations. And so when the system is linear, that means that each of the states can be expressed as a linear combination of the differential equation of the state can be expressed as a linear combination of the states. So x1 and x2 are the states. These are just parameters, a11, a12, and we can express the derivative in terms of those quantities. So it means that the function f1 is simply just this linear function. And the same thing can be done here for x2. And so we've written these suggestively because we can rewrite these two coupled differential equations that are linear in terms of a matrix now differential equation. So now we're going to lump together this quantity. So we'll define x as being the quantity x1 and x2. And so the derivative of x, so this part is derivative of x, and so this is just going to be a matrix A, and this is going to be x again. So we're going to have x dot is equal to A times X. And if you multiply these out, it's worth pausing the video, multiplying these out, and you'll see that after you multiply this matrix by this vector, you get indeed exactly this form. So that means that any linear system of differential equations, autonomous differential equations, can be written in this matrix form, just like this. Although we started with a very general type of differential equation and moved our way down to something more specific, these linear systems of autonomous differential equations are actually quite general and quite well used throughout engineering and science. And that's because many physical systems tend to be modeled by an F equals ma. And so oftentimes our states could be position, could be velocity, but if it's states, then A would just be, the acceleration would just be x double dot. If v is our state and it's the velocity, then the acceleration would be a single dot derivative. And so that means that oftentimes we represent our fundamental equations that represent dynamics of physical things, even electricities in circuits, oftentimes fall according to these simple type of equations. And so now if we had a situation like this, then that makes sense. We've kind of seen how you could set up a chain of these system of equations. If we have a second order differential equation, second order linear differential equation, or actually it could be arbitrarily high order, so it could be multiple derivatives, not just two. There's a nice simple way of converting a high order differential equation into a linear system. And so I'll just show you an example here, but this kind of describes why this approach, this linear system of autonomous differential equations, is actually quite general. So if I had a second order differential equation that looked like this, so the highest order is now derivative 2, but I also have a first order derivative and I also have y by itself. What I can do is I can define new states, x1 and x2, and the way you do this is you define the first state to be the variable of the ODE up here, and the second variable would be the next higher derivative, so that would be the first derivative. If you had a third order system, you would add y double dot as a third state. Effectively, once you solve a number of these out, you'll see that the order of the derivative tells you how many states you're going to need. So those two things are equal. So if we express x1 as y and x2 as y dot, then x1 dot is simply just, if we look back here, it's just y dot. And y dot in our new variables is just x2. So it just kind of feels like we're just rewriting things, but we're actually now what we've done is we defined x1 dot in terms of x1 and x2. And so in this case, x1 dot is just x2. If we do the same thing for x2, x2 dot will be now y double dot. And so notice that in this definition here, we have not introduced anything about the original differential equation except for our y variable. So this is where we get to inject the rest of the dynamics. And so if x2 is y dot, then x2 dot is y double dot. And if we look back at what y double dot is, we can just solve this, so y double dot, and we move everything else to the other side. It'll be minus alpha y dot, minus beta y. And so that's exactly what we've put here. Now the only last step we have to do is now we have to redefine this in terms of x1 and x2. So here, y dot is just x2, and y is just x1. And because this is a linear differential equation, that means that x2 dot is now still a linear differential equation. So these become our new dynamics in our new states. And notice now what we've done is we've taken a second order differential equation and converted into a system of first order differential equations where the number of states in the system is equal to the order 2. And so if we put this in matrix form, then there's no x1 term here times x1 plus 1 times x2. That's this first equation, and then this is the second equation. And so this gives you a way of, again, converting many types of physical systems, engineering systems, into a system of linear autonomous differential equations.